This is a short video on section 14.3 where we're doing double integrals in polar coordinates. Okay. So as was addressed in the previous video, the idea is that we need to change variables. Change variables is the goal. Okay. And essentially we have our original problem, we have our x and y are our old variables. Okay. And the idea is to write the original double integral in terms of new variables. And your new variables are typically given the letters u and v. And you can specialize the letters u and v to other letters if you are in more specific instances. So the idea here is that we want to look at polar coordinates. So polar coordinates is our change of variables, and the formula, what you must do in a change of variables problem is you must write the old variables in terms of the new variables. So you must write it in terms of two functions, t, I call them t1 and t2, in terms of u and v. And for polar coordinates, the function that you're going to choose is u times cosine of v and u times sine of v. So here is your formula which allows you to change variables. Okay. Now what we need to look at here, one way to view this change of variables problem is I like to put t1 and t2 as a function of u and v. So I like to make here a vector valued function in two variables. Okay, so it's vector valued. There are two entries to this vector, and each entry is a function of two variables. So this is a vector valued function. In two variables. Okay, the variables are u and v, vector valued, two entries. So in this case, our transform for polar coordinates, this is called the polar coordinates transform, is u cosine of v, u sine of v. Okay. And the idea, what one can visualize in this problem, is that this transform will take some region in the UV plane and transform it into a region in the XY plane. Okay. So it could look crazy over here. So here's some region in the UV plane. Oh, let me undo that. Let's call this script R, and this is the region R in the UV plane, which is the transform of the region R in the UV plane. So let's take a look at, I've done an example in class where we talked about how to transform, how to use this transform, and essentially the idea was to take like various lines in the UV plane, and when you transform them over, they will get transformed over to in the lines in the XY plane. And then when you transform this line, side of the rectangle, it became part of a circle, right? And if you transform this side of the rectangle, it will be this side of a rectangle, this side of a circle, and if you transform the top part, it will be a... So the idea here is to use this transform to create a new region, script ER, and what does the region look like in the XY plane. So I've got a better demo that can show how this all works. If you would like to go through the details, parameterize each side of this rectangle in terms of lines, use the transform, and then look at the resulting parametric form of what is created. So here we have a demo in Mathematica. It's on Calculus 3 demos from the Mathematica Demo Central. You can see here that there are a bunch of sliders for controlling this region, right, in the UV plane. So I am just creating a rectangle in the UV plane. Let me make this start at 0 here. Okay. And then the U variable, the largest value goes up to say 4, 4.5. You can see here that I'm creating a rectangle from 0 to about 5. And then V is a variable that controls the height of the rectangle in this direction. So if I start playing around with the minimum value of V and then the upper value of V, you can see that it's changing the size of the rectangle. And you can see that there is a correlation between changing the size of the rectangle and changing the shape over here in the XY plane. Okay. So what is going on there? What is going on is that U, let's adjust the U variable. Can you see that U is changing as the rectangle gets smaller and smaller? That is changing the size of this circle, right? Okay, so the largest value of the circle, the upper radius of the circle. So the upper radius of the circle is around 4 at this point. Okay. If you change the lower value of the rectangle, can you see this inner circle happening? That is a circle of smaller radius 2. So I have a circle of radius 4, and I have about a circle of radius 2. So this says to me that in this formula, U looks like it's a radius variable. Okay. In which case you would often then just call U equal to the letter R. You can give it a more descriptive name than just U. So you could use R for the radius variable. V, the variable V, should be controlling the size of the rectangle in the V direction. So here I am about V is equal to 0. Okay, let's let this be 0. Okay. And then change the upper value of V. Right, you can see I'm adjusting the variable V to about 2, 1.7, make it a little bit bigger. Can you see that it's controlling how much the circle, the angle variable of the circle, how much I'm going around in the theta direction? How much you can see as V gets to 4, that's about 3 pi over 2. As it gets closer and closer to 6, right, 6.28, that is about 2 pi. So what we can see here is that this rectangle, okay, gets transformed under this transformation, the polar coordinates transformation, gets transformed to this little annular region, this region that is the region between two circles, and how far it goes around is controlled by the variable V. So if I want V to be about 3.14, which is about pi, that would be about half of the circular region. Okay. So this lets us know that the variable V is like an angle variable. And therefore we should give it a name of an angle, and typically we use the letter theta for that. Okay. If you're in physics, they may use phi instead, phi or phi. But in math, we typically use theta for this variable. Okay. So there's our polar coordinates transformation. The goal in our problems is to try to do a double integral in the xy plane over some sort of region that looks like this annular region. And the goal would be to transform this double integral in the xy plane to a double integral in the UV plane. And I hope you can see the advantage here, the advantage being that the region in the UV plane that you need to integrate over is simply a rectangle, rather than this complicated annular region, which would involve a bunch of square root functions in your limits of your integral. So if you do want to try to do this integral, you're going to be stuck with a lot of square roots. But if you try to transform, you will have, maybe a function that's got some sines and cosines in it, but you will be integrating over a function that is just, the limits of the integral would just be over a rectangle in the UV plane. So that would be a significantly, most likely, easier integral to compute. So actually computing an integral in polar coordinates would be the subject of the next video.